Welcome back, my students. Dr. Ogwe here, and we are studying the physiological characteristics of cardiac muscle. In the previous two videos, we studied first 6 physiological characteristics. Now, in this video, we are going to study the physiological characteristic number 7th and 8th clearly. And before we start with this chapter, with this topic, I would like to tell you that my handwritten notes of this video are in the description of the lecture. Go check it out. So let's begin. We have the physiological characteristics of cardiac muscle. Number 7th, it states it is called the Frank-Starling law of the heart. Frank-Starling law of the heart. Before we study what does this Frank-Starling law of the heart means, we need to know 3 terms. Number first term is the end diastolic volume. End diastolic volume. End diastolic volume means the amount of blood in ventricles before contraction. Clearly, this is the diagram of the heart. This is the left ventricle and this is the right ventricle. Clearly, so the amount of blood in the ventricles, before contraction, before ventricles contract or systole is called end diastolic volume. So amount of blood in ventricles before contraction. Number second term we have here is the preload. Preload is the end diastolic pressure which is stretching the walls of ventricles. We know there is blood in the ventricles. This blood is exerting a pressure on the walls of the ventricles. This pressure is called preload. So preload is the end diastolic pressure. This preload has another definition. It states the degree of the tension on the muscle when it begins to contract. So when the muscle begins to contract, when the heart muscle begins to contract, it exerts a tension on muscle. It exerts a tension on muscle because there is blood in the ventricles. There is blood in the ventricles. This blood is exerting a tension on the walls of the ventricles when ventricles contract. That's called preload. Now there is third term that's called afterload. Afterload is the load against which muscle exerts its contractile force. In the heart, in the ventricles, there is blood. So this load against which the heart is exerting its contractile force, that's called afterload. There's another definition of the afterload. The afterload of the ventricles is the pressure in the aorta leading from the ventricles. We know that this is the left ventricle gives blood to the aorta. Clearly, so when the ventricles contract, they exert a pressure on the blood. This blood is thrown out into the aorta. Now in this aorta, this blood is exerting the pressure on the walls of the aorta. Clearly, so that pressure is called afterload. The afterload of the ventricles is the pressure in the aorta. So the pressure in the aorta leading from the ventricles. So when the ventricles contract, this left ventricle, it gives blood to the aorta. Now blood goes into the aorta, and that blood in the aorta is exerting the pressure on the walls of the aorta. That pressure is called as the afterload. Clearly, so these are the 3 terms that we needed to know. Now we have the Frank-Starling law of the heart. Frank-Starling law of the heart states the force of contraction of the heart is directly proportional to the end diastolic volume and end diastolic pressure within physiological limits. It states more is the end diastolic volume, more is the contraction of the heart. Less is the end diastolic volume, less is the contraction of the heart, force of contraction of the heart. So if there is, what is end diastolic volume? Amount of blood in ventricles before contraction. So if there is more volume, of blood, the force of contraction of the heart will be more. If there is less blood, the force of contraction will be less. So that is what is the Frank-Starling law of the heart. Force of contraction of the heart is directly proportional to the end diastolic volume. If we plot a graph between the end diastolic volume on the x-axis versus force of contraction on the y-axis, we get a straight line. We get a direct proportion relationship. More the end diastolic volume, more is the force of contraction of the heart. Simple. Clearly. So what is the reason? If more is the end diastolic volume, more will be the end diastolic pressure. Clearly. So more volume in the ventricles. Clearly, more pressure they will exert on the walls of the ventricles. So more is the end diastolic volume, more will be the end diastolic pressure. As a result, this heart muscle will stretch due to the more pressure. Clearly, so that's why I stated greater the end diastolic volume, greater the corresponding end diastolic pressure, and greater is the stretch of cardiac muscle. So greater the pressure, so greater is the stretch of cardiac muscle. Clearly, so when this cardiac muscle stretches, there is more endodiastolic volume, more will be the pressure on the walls of the ventricles. Now this cardiac muscle, it stretches. Now this cardiac muscle stretches. Now due to the stretch of this cardiac muscle, its sensitivity to calcium increases. Its sensitivity to calcium increases. When it is sensitivity to calcium increases, there is the more contraction, there is more force of contraction, there is more force of contraction. So that's what I stated here. Myocardium will be stretched due to the greater volume. So greater will be the volume, myocardium will get stretched. Now when it gets stretched, the sarcomere length will increase. The sarcomere length will increase. Now if the sarcomere length increases, it will result in increased sensitivity to calcium. Now due to the increase in the sarcomere length, the calcium sensitivity will increase. When the calcium sensitivity will increase, therefore a much stronger contraction. There will be the stronger contraction of the heart muscle. There will be the stronger contraction of the heart muscle. So this is what is Frank-Starling law of the heart. In simple words, force of contraction of the heart is directly proportional to the endodiastolic volume, and this is the graph. Clearly? So this is the graph. This is the same graph, the previous graph. On the x-axis we have endodiastolic volume, and on the y-axis we have the force of contraction, and we can see there's a direct relationship. Clearly, now there are some factors. Now there are some factors which can alter this graph. For example, the positively inotropic factors will increase the force of contraction. Look at here. This is the endodiastolic volume. Clearly, so at this endodiastolic volume in the normal graph, this is the force of contraction. So this is the force of contraction. Now due to the positively inotropic factors, the force of contraction will be more. What are inotropic factors? Inotropic factors are those factors which increase the contractility of heart. So if there is more contraction, so there will be the more force of contraction. So positively inotropic factors increase the force of contraction. Clearly here. Now look at here. This is the same endodiastolic volume, but the force of contraction in this graph is here. So there is a decrease in the force of contraction due to the negatively inotropic factors. Simply, positively inotropic factors will increase the force of contraction of heart, whereas negatively inotropic factors will reduce the force of contraction of the heart. This is the normal graph. This is the graph in positively inotropic factor. This is a graph in negatively inotropic factor. Now, what is the example of positively inotropic factor? That is, the example is increased sympathetic activity. We know our heart is supplied by nerve fibers. Those nerve fibers can be sympathetic nerve fibers. Those fibers can be parasympathetic nerve fibers. So if we stimulate those sympathetic nerve fibers, clearly there will be increased sympathetic activity. Clearly, and it is an example of positively inotropic factor, what is a positively inotropic factor? Which increases the contractility of heart from here to here. Clearly, and negatively inotropic factors, example of negatively inotropic factor is reduced sympathetic activity. Clearly, so this is the graph, modification of the length and the force of contraction in the relationship by inotropic factors. So what is this graph? How does inotropic factors alter the force of contraction and EDV? Clear? Now, before moving on to the next point, a simple point, sympathetic nerve fibers. I told you that our heart is supplied by sympathetic nerve fibers. What are sympathetic nerve fibers? Those originate from the thoraco-lumbar portion of the spinal cord. Those nerve fibers which originate from the thoraco and lumbar portion of the spinal cord are called sympathetic nerve fibers, and those fibers that arise from the cervical and the sacral portion of the spinal cord, those are called parasympathetic nerve fibers. So our heart is supplied by sympathetic nerve fibers as well as parasympathetic nerve fibers. Sympathetic nerve fibers originate from the thoraco and lumbar portion of spinal cord, while as parasympathetic fibers originate from cervical and sacral portion of the spinal cord. This is an important term. This is an extra point that you need to know. Clearly, put it in the box and highlight it. So simple. This is the direct relationship between the EDV and force of contraction of the heart. And we get a graph like this, and positively inotropic factors like increases sympathetic activity make the graph like this, while as negatively inotropic factors make the graph like this. Clearly, so this is the Frank-Starling law of the heart. Physiological characteristic number 7th. Now we have the last physiological characteristic number 8th, that's called the all or none law of the heart applies to the entire syncytium. Clearly, what does this statement mean? We know our cardiac muscle, this is the heart. It's made up of cardiac muscle. That cardiac muscle behaves like a syncytium. What do you mean by syncytium? It means all the muscle cells are so connected that they behave as a single unit. You know, this is heart, it's made up of cells. These cells are so connected that they behave as a single unit. All they behave as a single unit. clearly. So as a result, when we give a stimulus to any part of the heart, but that stimulus should be a threshold stimulus or greater than threshold stimulus, clearly. So when we give a stimulus of threshold or greater than threshold intensity in any part of the heart, in any part of the syncytium, it will result in the contraction of the entire syncytium. That means if I give a stimulus here, clearly the whole of the heart will contract, so heart behaves as a single unit. That is what I stated. The all or none law of the heart applies to the entire syncytium. If all the heart behaves like a single unit, if we stimulate a single part, it will result in the contraction of the whole heart. Clearly. So these are the first 8 physiological characteristics of the heart. Now if we go in the guidance, this is the so this is what we studied in this video. I'll show you. So this is the graph, this is the end diastolic volume, and this is the force of contraction of the heart. As we can see, here is the direct relationship, and due to the positively inotropic factors, the graph is increased, height of the graph increases, and due to the negatively inotropic factors, height of the graph decreases. Thank you very much. Dr. Uwe here. Like this video, share this video with your mates, comment on the video. Thank you very much.